Welcome to our Quantum Deep Dive.
Great to be here.
Today we are plunging into a truly fascinating area. Think light becoming sound and quantum physics unlocking completely new ways of seeing things.
Yeah, it's really cutting edge stuff.
We're doing a deep dive into quantum photoacoustic imaging, and we're drawing our insights, importantly, only from an essay by Jorgo Schneepath.
That's right. And you can think of this technology as taking the core idea of classical photoacoustics, the basics.
Okay.
And then giving it this powerful upgrade using the strange and often counterintuitive rules of the quantum world.
So our mission today?
Our mission is really to unpack the key principles, look at the tech breakthroughs, where it could be, use the applications, and what the future might hold, all based on what Schneepath lays out for us in the essay.
Okay, so let's start there with that classical foundation. How does, regular photoacoustics actually work?
It's pretty elegant, really. You shine a short pulse of light onto something, could be tissue, a material, whatever you're trying to image, and that light energy gets absorbed. This causes that specific part of the material to heat up incredibly quickly.
Right. Very fast.
Very fast. And that rapid heating makes it expand just a tiny, tiny bit, but enough to create a pressure wave.
Ah, so like sound.
Essentially, yeah, a sound wave. The essay calls this the thermoelastic effect.
Thermoelastic effect, okay. Like tiny sonic booms happening inside the material.
Exactly. That's a good way to put it. And the strength of that sound wave, well, it tells you something important.
Like what?
As the essay points out, the pressure generated, let's call it P, is directly related to a few things. First, how much light the material absorbs, that's I.
Okay, absorption.
Then the energy of your light pulse, E. And finally, a property of the material itself called the Grüneisen coefficient, gamma.
Gamma? What does that represent again?
You can sort of think of as how efficiently that specific material turns heat into pressure into that sound wave.
I see.
So, more absorption or more laser energy means a stronger sound signal coming back at you.
Okay, that seems pretty straightforward. Light goes in, makes heat, makes sound, and then we listen for that sound.
Exactly.
But how does adding the quantum part, supercharge this whole process?
This is where it gets really interesting. Quantum physics, it adds entirely new dimensions to this. It brings in these concepts like entanglement, superposition, coherence.
Things that just don't exist in the classical world.
Precisely. And they let us manipulate light and how it interacts with matter in ways that give us real imaging advantages.
Okay, let's pull out the specific quantum ideas that Schneepath focuses on here. First one up. Wave-particle duality.
Yeah, this is fundamental. The idea that light and actually even particles of matter can behave as both a wave and a particle simultaneously.
Why does it matter for imaging, though?
Well, because at the quantum level, those light particles, photons, they carry information. Understanding them as both waves and particles lets us work with the information that's embedded in the light on a really microscopic scale. And that's crucial for achieving resolutions that are just, beyond what classical limits allow.
Okay. And then you mentioned superposition and quantum coherence.
Right. So superposition is that famous quantum ability to be in multiple states at the same time, kind of like being in several places at once, metaphorically speaking. And coherence is when these different quantum states maintain a specific stable relationship. This allows them to interfere with each other in predictable ways.
Interference. How does that translate into an imaging benefit? That sounds almost like noise.
But it can be constructive interference. See, superposition can let you process information encoded in different quantum states all at the same time.
Okay.
And coherence means those multiple quantum paths or possibilities can combine, they can interfere constructively to build up a much stronger, much cleaner signal than you'd get classically, just adding things up.
Interesting.
So this improves the signal strength, and it also helps make the final image reconstruction more accurate.
So it's not just about using, say, brighter light or listening for louder sound.
Yeah.
It's about using the quantum properties of the light and the system itself to get fundamentally better data.
Precisely. And this feeds directly into things the essay mentions, like quantum-enhanced signal processing, by using these quantum phenomena, particularly things like entangled photons.
Entangled photons, those linked particles.
Exactly. Pairs of photons that are linked together no matter how far apart they are. Using them can dramatically boost the signal-to-noise ratio, the SNR.
Right.
Schneepath also highlights that using coherent light sources, laser-like sources, inherently minimizes noise right from the start. And the coherence itself helps sharpen the resolution.
And it's not just about the special light you send in, but also the sensors listening for those returning sound waves, right? They have to be special too.
Absolutely. You need detectors that are sensitive enough to pick up those potentially very faint quantum-enhanced signals. The essay talks about new types of sensors, like ones using quantum dots or even superconducting elements.
Superconducting, wow.
Yeah, these are incredibly sensitive. They can detect much weaker acoustic signals than classical sensors, which expands the range you can image and pushes the resolution further. It's really about hearing those very quietest echoes from the quantum interaction.
Okay, so we've got the theory down. Light makes sound, quantum weirdness enhances the signal and the information content. Let's talk tech. What are the actual components that make up one of these quantum photoacoustic systems?
Well, the heart of it often involves a quantum light source. You need light that has these specific quantum properties we've been talking about.
Like the entangled photons you mentioned.
Exactly. Entangled photons are a prime example Schneepat mentions. And their benefit is huge. They carry a high density of information. They give you that boosted signal-to-noise ratio we talked about.
Mm-hmm.
And crucially, they can enable imaging even in very low-light scenarios, situations where a classical system might just see noise because the signal is too weak.
And how do you make these entangled photons?
Technologies like parametric down conversion are used. It's mentioned in the essay.
Parametric down conversion. That sounds complex.
It is a complex process, yes. And actually, that's one of the technical hurdles we can talk about later. But basically, think of it as a special crystal that can split one incoming photon into two lower energy photons, but these two new photons are entangled.
The twins.
The entangled twins, exactly. They're key to the quantum advantage. And alongside those special sources, as we said, you need those advanced quantum sensors, superconducting detectors, quantum dot sensors designed to capture every tiny bit of acoustic information generated.
Okay, so you've generated the quantum light, sent it in, detected the subtle acoustic waves with super sensitive detectors. Yeah. How do you make sense of all that data then?
Right, that's where quantum algorithms come into play. The essay discusses how algorithms based on quantum mechanics are used to process those acoustic signals. A key one mentioned is the quantum Fourier transform, or QFT.
QFT, like a classical Fourier transform, but
yes.
Quantum.
Exactly. The classical Fourier transform is already great for analyzing wave patterns. The QFT can do this even more efficiently, especially on quantum computers, although classical processing benefits from quantum insights too. Applying these quantum approaches means potentially faster, more accurate processing.
Especially with weak signals.
Especially important when you're dealing with those weak but very information-rich quantum signals. This all leads to a better reconstruction of the final image from the data.
So, let's put it all together then. You've got the quantum light, the ultra-sensitive sensors, these smart quantum algorithms.
Yeah.
You get real, measurable improvements in the images you can produce.
That's the goal. And Schneepat connects these developments directly to practical benefits. Things like better spatial resolution, meaning you can see much finer details in the image.
Sharper pictures?
Sharper pictures, yes. And higher sensitivity. That allows you to detect really subtle differences in, say, material properties or tissue absorption that classical methods might completely miss. And overall, you get a reduction in noise, which gives you much cleaner, clearer images to interpret.
That sounds like a really powerful combination of advantages.
Yeah.
So, just to sum up the comparison, compared to classical photoacoustics, the quantum version offers potentially higher sensitivity, better image quality, maybe more efficiency, even with lower energy input.
That's the promise, yeah.
But technology that's cutting edge,
yeah,
it must have its challenges, right?
Yeah.
What are the practical hurdles that Schneepat points out in the essay?
Oh, definitely. There are significant ones. On the pure technology front, scalability is a major issue.
Making it bigger, cheaper?
Exactly. Getting those complex quantum light sources, like the ones using parametric down conversion, to work reliably and affordably on a large scale, that's not easy. And the entire system, the sensors, the light sources, the control systems, it's often very costly and complex, sometimes requiring specialized infrastructure, like the essay mentions cryogenics, super cold environments for things like superconducting components.
Right, that's not exactly plug and play.
Not at all.
And are there maybe scientific or even broader questions that come with a technology this powerful?
Yes, the essay brings up both aspects. Scientifically, there's the inherent uncertainty you always find in quantum measurements. It even mentions the famous Heisenberg uncertainty principle.
The GUC one.
That's the one. Expo greater than or equal to 2. Basically, it tells us there's a fundamental limit to how precisely you can know certain pairs of properties, like position and momentum, simultaneously in the quantum realm.
And that affects imaging.
It does. This uncertainty creeps into the measurements and requires sophisticated error correction techniques to manage and get reliable results.
Okay. And the broader issues.
Well, there's also the potential for misuse. Like any powerful imaging technology, this could hypothetically be turned towards surveillance or military applications, which really highlights the need for careful thought about ethical guidelines as the technology develops and becomes more capable.
Those are absolutely crucial points to keep in mind as the field moves forward. But let's switch gears back to the exciting potential. What about the applications Schneepat describes? Where could we realistically see quantum photoacoustic imaging making a real impact?
The list is actually pretty diverse, which is interesting. In biomedical diagnostics, for instance, it seems to have enormous potential.
Like for doctors.
Exactly. For instance, in cancer detection, its enhanced sensitivity could allow for much earlier detection by spotting really subtle differences in tissue absorption or density that might indicate a developing tumor.
Ah, catching it sooner.
Precisely. Remember that formula we talked about? SAUEE? This tech is really optimized to pick up even tiny variations in that absorption coefficient within biological tissues.
So it's about seeing those critical changes non-invasively and potentially much earlier than current methods allow.
That's the hope, yes. The essay also notes its potential for imaging soft tissue and blood vessels generally. You could potentially measure things like oxygen saturation in blood non-invasively.
Which would be useful for?
Oh, monitoring cardiovascular health, checking blood flow during surgery, diagnosing conditions related to poor circulation. Lots of possibilities there.
Okay, so big potential in medicine. What about beyond medicine? Where else does Schneepat suggest it might show promise?
Well, in material science and also industrial inspection. For nanomaterials, for example, it could analyze their unique properties and even look at molecular fluctuations with incredibly high precision.
Which helps develop new materials.
Exactly. It's key for designing and verifying next-generation materials. And industrially, it could be great for non-destructive fault analysis.
Like finding flaws without breaking things.
Right. Finding hidden cracks or stress points inside components, which could improve safety and extend the lifespan of parts in aerospace, manufacturing, you name it.
And Schneepat even mentions security and environmental applications.
Yes. For security, the idea is it could potentially detect explosives or hazardous chemicals by analyzing their distinct light absorption signatures, their optical fingerprints, even at very low concentrations.
Wow.
And environmentally, it offers a potential way to monitor pollutants non-invasively. Things like CO2 or methane in the air or contaminants in water or soil, again, by detecting their specific absorption characteristics.
That truly is a broad range of potential uses. It really highlights the versatility this kind of quantum-enhanced technology could bring. So as we bring this deep dive towards a close, what's the sort of core takeaway message and the general outline for quantum photoacoustic imaging?
I think the core message is pretty clear from the essay. By fusing classical photoacoustics with these fundamental quantum principles, we're creating or starting to create a genuinely new imaging modality, one with capabilities that could go far beyond what was previously possible.
Right.
And it seems applicable across incredibly diverse fields. Schneepat really emphasizes its significance in potentially revolutionizing areas like medical diagnostics, material science, and environmental monitoring.
And looking ahead, what does the future hold, according to the essay?
The outlook seems to be one of rapid evolution. The essay points towards potential breakthroughs coming from improving those quantum light sources, making them more practical, integrating the systems with AI and machine learning for even smarter data processing and interpretation, working towards making the systems more compact, maybe even portable eventually.
Portable quantum imaging. That would be something.
Wouldn't it? And also finding synergies with other emerging quantum technologies like quantum communication for secure data transfer or other types of quantum sensing. It really feels like a field that's on the cusp of some significant advancements.
It really sounds like we're just scratching the surface of what might be possible here.
I think that's fair to say, yes.
So let's leave our listeners with this provocative thought, inspired by this deep dive into Jirgo Schneepat's insights. If we continue to develop technologies like this, ones that can reveal the hidden properties and, tiny fluctuations of matter right down at the fundamental quantum level, how might that fundamentally change how we understand health, how we design materials, or maybe even how we approach security in the years ahead?
That is a fascinating question to ponder for sure.
And with that, we wrap up this deep dive into quantum photoacoustic imaging, drawing on the insights presented in Yurgo Schneppant's essay. Thank you so much for joining us.
Goodbye.